Hey guys, welcome back to my kitchen, and in this lab we're going to be looking at the effects of concentration and temperature on the processes of diffusion and osmosis. So just to recap, you might remember some of the ways in which molecules can cross a plasma membrane of a cell. So we have diffusion, which is where molecules move from an area where they're more highly concentrated to an area where they're less concentrated. So if there's a difference in the concentration of these molecules on either side of a plasma membrane, we say that there is a concentration gradient set up. So diffusion, molecules want to go from an area of greater concentration to an area of lesser concentration. Osmosis is also diffusion, but it's diffusion specific to water. So osmosis is where water molecules go from an area where they're more highly concentrated to an area where they're less concentrated. So, lecture which I posted will explain these processes in more detail. So this is kind of just a recap. You might also remember that not all molecules can just pass through the plasma membrane down their concentration gradient. Some molecules are big or they have a particular charge. That means that they need help crossing that plasma membrane. So in many cases, there will be proteins embedded in that plasma membrane that the molecules can use as kind of gates to pass through into or out of the cell. In that case, that kind of process by which the molecules use the proteins to cross the plasma membrane is called facilitated diffusion or facilitated transport. Sometimes it's called passive transport. And the other kind of way that things go across the membrane is sometimes they want to go against their concentration gradient. So instead of going the natural way where they'd go from an area of greater concentration to lesser, they do the opposite, where they go from an area of lesser concentration to greater concentration. To do that, it requires energy in the form of ATP. Well, today we're going to keep it simple. We're just going to look at diffusion and osmosis as molecules would naturally go from an area of greater to lesser concentration. But we're also going to consider the fact that plasma membranes are selectively permeable. That means they can choose which molecules they want in and which ones they don't. If a molecule is too big and it doesn't have a transport protein, then it is actually not going to go through that plasma membrane. So we're going to be illustrating the plasma membrane in this lab using a funky little plasticky material called dialysis tubing. So in your lab in a box kit, you want to find this bag that says dialysis tubing, and this right here is your dialysis tubing. So let's open it up. Now they've provided you with a good amount of this stuff. This is 10 feet of dialysis tubing. We're going to have to cut this baby into pieces. So you're going to need 7 pieces of dialysis tubing for this lab, and you want each piece to be about that big, maybe about 7 inches or so. Now, as you're preparing these things, you might find it's a little difficult to do with gloves on, but so if you need to take your gloves off to work on this a little bit, you can. We're not working with anything real dangerous today. So see if you can get your dialysis tubing unraveled here. I'm going to pause this for a sec. Okay, wow, that tape was stuck on there. They're strong. Okay, so I'm unraveling this dialysis tubing, if you guys can see this here. And when you first look at it, it just looks like a piece of plastic tape, but it's actually a tube. And in order to make it a tube, we're going to have to soak it in some water. So first thing we're going to do, let's go ahead and cut our pieces. So we're going to need 7 pieces, again, about 7 or so inches long. So I'm going to cut mine to be about that length. Okay, so I'm going to make them all the same length. So let's do 1, 2, and then I'm going to pause this for a sec. I'm going to fold this over 7 times so I can cut 7. Okay, I have all these things folded up here, so now I can just easily, I'm just going to easily cut these into about 7-inch pieces. Okay, I have my approximately 7-inch pieces of dialysis tubing here, and now I'm ready to make my tube baggies. So first thing I want to do is just grab one of my plastic cups. So you're going to need 6 of these. You're going to need 6 clear plastic cups. These come in a big thing of them, so pretty cheap. So there's just plastic cups. You're also going to need 1 glass cup, and that's for the treatment where we have to stick it in boiling water. You don't want to stick plastic in boiling water. So to get started, let's just take one of these cups for now and just pour a little water inside. And take one of these pieces of dialysis tubing and just dunk it in there for about 30 seconds. Because this is going to get the tubing nice and wet so that you can actually open it up and make these baggies. All right, so get it nice and wet, and at that point you should be able to kind of use your fingers to, let me see if I can get the camera to see what I'm doing here. Just kind of rub it in your fingers until you can get that tube to open up. So if you can see here, I have a nice opening in the tube. Can you guys see that right there? There's an opening in the tube. So it becomes a baggie, and eventually you're going to want to do this to both ends, but we're going to start off with the first end. And now that it's wet, what I'm going to do is I'm going to fold down, we want about 4 centimeters, folded down, twisted, and sealed with a nice tiny rubber band. So these are the rubber bands I bought. I got these from Walmart, and they're really, really tiny. The tinier, the better. So you want to get these little tiny rubber bands just to kind of give you an idea of how small those are. So what I'm going to do is I'm going to take that end that I opened up. I'm going to start folding it down. So I'm going to fold it down about 3, 4, 5 times, squish it, and twist it. Okay, because we don't want any leakage getting out here. So you want to make it nice and twisted, and then take that little rubber band and just twisty, twisty, twist. Just keep twisting. Make sure there's no opportunities for any liquid to leak out of the bottom of this tubing here. Okay, so we're going to do that. That's pretty good. So I don't believe anything's going to leak out of that. Now, I haven't talked to you too much about this tubing. This tubing, I think I did mention that it represents the plasma membrane of a cell. And it does so in a pretty good way, because just like your cell membrane, this dialysis tubing is selectively permeable. And that's because it has little microscopic pores in the plastic. So small molecules like water can just diffuse in and out through osmosis. But large molecules, like sugar molecules that you might find in something like molasses, can't get through those pores. Ding, 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 hint, hint. The molasses cannot get through the pores. It cannot cross the plasma membrane, or in this case, the dialysis tubing. Keep that in mind. That's going to be important for interpreting your results. Hint, hint, hint. Okay, anyway, back to this. Okay, so we got one end tied off there, making sure there's no leaks. I'm going to dip the other end in the water again just to soften it up just a little bit more. So you can see what I'm doing there. And again, opening up the tube on the other end. Come on. Sometimes it's a little tricky to do with gloves. Okay, but I got mine. All right, so now you can kind of stick your finger, or better yet, a pipette into the tube just to open it up a little bit. Okay, now we're good. All right, so what we're going to be doing with this is we're going to have 4 different treatments for the first part of the lab, and that's for the effective concentration on diffusion and osmosis. And we're going to have 4 concentrations of molasses inside these tubes. We're going to have a treatment of 0% molasses, meaning 100% water, 25% molasses with 75% water, 50% molasses with 50% water, and a final treatment where it's 100% molasses in our dialysis tubing. So let's go ahead and label our cups with our concentration treatments. I got my trusty permanent marker here, so I'm going to write 0%, and again, keep in mind this is 0% molasses, 100% water. Let's see if I got my treatments right here. Okay, so this is my 0%. I have 25%. I have, oops, that one has a half in it. What's that? 50% molasses, 50% water, and 100% molasses. Okay, so here are our 4 treatments for concentration. Again, we're looking at the effects of concentration on how molecules diffuse across this dialysis tubing representing our plasma membrane of our cells. All right, now what I need to do is I'm going to put 100 milliliters of tap water into each of these treatments. So that's going to be our environment, our water environment for our dialysis tubing. So I have here my trusty graduated cylinder. This is the 100 milliliter graduated cylinder. I have some tap water around. So I'm going to use my proper methods for measuring things in a graduated cylinder to measure exactly 100 milliliters and put them in each one. So I'm going to show you the first one. So just, it's kind of messy. Pour in the water into the 100 milliliter beaker or graduated cylinder. Make sure you're reading the bottom of the meniscus. Make sure the bottom of the meniscus is right at 100 milliliters. Mine is. See if you guys can see that. Okay, and now I'm going to pour it into the cup. Okay, now I'm going to repeat that same thing with the other three. Be right back. Okay, so I have 100 milliliters of water into each of my 4 treatments here, and now it's time to make my little baggies. This is going to take some time. I'm going to need 4 different dialysis tube baggies for each one of these at the proper concentrations. Okay, so I'm going to want 2 of these transfer pipettes to be able to work with, one to use for water and one to use for molasses. So you might remember how to use these things. You squeeze the top, stick it in the medium, slowly release the top to pull it up, and then transfer the stuff by sticking the tip of the tube in and squeezing the top to release the contents. So I'm going to start with the 0% molasses one, the one that's 100% water. So I'm just going to take an extra cup of water here, and I'm going to just scoop up the water with the transfer pipette, stick the tip into the opening of the dialysis tubing, and squeeze. And I'm going to let this first one determine how large I'm going to make all of my dialysis tube baggies, because you want them to all be approximately the same, more for making sure that you have the same approximate size in there, just to kind of standardize everything. Okay, so I'm going to make it a little bit bigger. I'm going to put in, let's see, maybe 4 squirts of this stuff. Keep adding it. And 1 more. So that was 3 squirts. And 4 squirts. Okay, so I've stuck in here 4 squirts of water, which is, each one of these is holding 3 milliliters, so about 12 milliliters of water in there. But okay, so once I have that done, to complete the dialysis tubing bag, I'm going to fold over the other end, just as I did before. Try to squeeze all of the air out first. Fold it over, pinch it, and start twisting it, and then we're going to need another rubber band to complete the process. So twist it real good. Again, you don't want any leakage going out. I'm going to grab another rubber band. Bring this up for a sec. Okay, so grab another rubber band, and again, make sure you're wrapping this thing really good, because you don't want any leakage going out. And again, the hardest part is trying to get rubber bands on when you're wearing gloves. Not an easy task. They should have PhDs just for that. Okay, so I have my nice dialysis tubing. This is the 0% molasses, 100% water treatment. Now, I don't want to stick this into my cups yet. I want to figure out what volume exactly of liquid did I just put into this little baggie here. So to figure out, oh, and by the way, it's not really that important at this stage to use your goggles, because we're just working with water and molasses. We haven't gotten into any glass yet, really. But when I put stuff onto the stove, that's when the goggles are going to be critical. But I'll go ahead and leave them on for good practice. So I want to figure out what is the volume inside of my dialysis tube baggie. Well, it's kind of a weird shape, kind of hard to measure. So we're going to use a method called the volume displacement method. It's quite simple, actually. You're going to need your 100 milliliter graduated cylinder. And what we're going to do is we're going to fill the graduated cylinder up with 50 milliliters of water. So I'm going to go ahead and do that right now. And I'm just going to use this cup to pour in 50 milliliters. Okay, so I have exactly, and you want it to be exact, I have exactly 50 milliliters in my graduated cylinder, 50 milliliters of water. And now what I'm going to do is I'm going to take my little dialysis tube bagging and I am going to gently drop it into the graduated cylinder. And you'll notice that the volume of water in the graduated cylinder has risen. In fact, mine has risen to 59 milliliters. Okay, so if you guys can see that, so it's gone from 50 to 59 milliliters. And so what that means is that my final volume was 59, my initial volume was 50. That means 59 minus 50. That means that the volume inside of the bag was 9 milliliters. Okay, so I'm going to spill that water back out to retrieve my little guy here. Okay, so this guy I figured out through the volume displacement method has an internal volume of 9 milliliters of liquid. Okay, so that was using the volume displacement method. Now I'm going to want to blot this guy really well and dry him because I don't want the extra liquid on the outside from doing that procedure to affect my results. So I'm going to go grab some paper towels. I will be right back. Okay, I got my paper towels here. I'm just going to gently blot the outside of this guy. Okay, and then I'm going to let him sit aside because I don't want to add him to these cups until I'm ready to add all 4 of the dialysis tubing to the cups. So I'm going to let that guy rest aside. Now I got to make 3 more dialysis tubings just for this part of the experiment, the effective concentration on diffusion. Then I'm going to have to make another 3 for the effective temperature. So this could take a while. So if you want to get all of your dialysis tubing set up for the whole lab, you can do that. So this was the 0% molasses treatment. Now I'm going to work on one that's 25% molasses and 75% water. So I have my molasses I got from the grocery store here. Now this stuff is thick, so your normal pipette is going to be a pain to try to suck up and release that molasses because it's really tapered and narrow at the bottom. So I have a second pipette that I'm going to use just for molasses. So I have some scissors here, and what you're going to want to do is just cut off the end of this pipette, and now you have a nice wide opening for sucking up the molasses. So that works much nicer. Okay, so same kind of thing. Grab another piece of your measured dialysis tubing here. So we had pieces that were about 7 inches. Okay, so grab your dialysis tubing, same kind of thing. In an extra cup of water, you want to soak it for about 30 seconds. And then we're going to fold down the end and put a rubber band on it, just like we did before. Everything's going to be the same, just like we did for this other one, and we're going to try to make it about the same size as this. The only difference is we're going to take the bottom quarter of the inside and fill it with molasses, and then take the other pipette and fill up the other 75% with water, and then tie the other end. So I'm going to make my second tube, and I will be right back. Okay, so I got the end of the second piece of dialysis tubing here. I'm going to go ahead and add my molasses. So I want to add 25% molasses. And this stuff gets kind of messy, so you probably want some paper towels around. You want to go ahead and stick the pipette down towards the bottom so that you're not filling up the sides with this stuff. So for this one, remember that I used 4 squirts of water for the first one, so it would make sense to kind of use that as a basis here. Okay, and let it sit for a sec so that you can figure out how much is going to drip down from the sides. Okay, so if I have that much molasses at the bottom, I want to fill the water up to about here so that I have 1/4 molasses to 3/4 of water. So now I'm going to take my water pipette, and this should be 3 squirts of water since we used 4 for the 100% water. 2 and 3. Okay, and then we're going to fold down the other end just like we did before. So I will be right back. I'm going to tie that up. Look how beautiful that is. See, this is my 25% molasses treatment. I have 1/4 molasses, 3/4 water. So this is 25% molasses treatment. So same kind of thing. I need to take an initial volume of this. So volume displacement method again. How do we do it? Fill this with 50 milliliters of water. Gently place this into the water. See how much the volume in the graduated cylinder moves up. Subtract that final volume from the initial. That tells me the volume of liquid inside of here. So I'm going to do that. I will be right back. Okay, so I took my initial volume inside of this little baggie using the volume displacement method. And it turns out this particular one has a volume of 10 milliliters. So now you want to make sure that you're recording your initial volumes into the data table inside your lab handout. So data table A, there's a column for initial volumes. That's the initial volumes inside of these tubes. So I would record 9 for this one and 10 for this one. Based on my results, your results will likely be different. All right, so I have my 0% molasses treatment, my 25% molasses treatment. Now I need to make a baggie that'll be 50-50, 50% molasses, 50% water. So I'm going to use the same methods to do that, except I'm going to fill half up with molasses and half with water. So I'm going to go do that. I will be right back. Okay, here's my 50-50 concentration treatment. So you can see that there's about 50% molasses to 50% water. Now what do I have to do? That's right, I have to take my initial volume inside this baggie using the volume displacement method. So again, fill the graduated cylinder up to 50 milliliters, gently drop the baggie into the 50 milliliters, and see how much the volume in the graduated cylinder goes up. Then subtract that final volume from the initial 50 milliliter volume, and that will give me the volume of liquid inside this bag. Let me do it. I'll be right back. Okay, I got 8 milliliters for the volume of my 50-50 treatment. And remember, so now I have 3 bags. My 0% was 9 milliliters. My 25% was 10 milliliters. And my 50% happens to be 8 milliliters. So don't worry about that. These initial volumes are slightly different from each other, because at the end of the experiment, we'll be taking the final volumes of these guys and subtracting to determine the change in volume inside these dialysis tubing baggings. And that's important because that change in volume is going to tell us what's happened to these substances, water and molasses. Have they gone into the bag, out of the bag? Did one do one thing and the other do another thing? That's what we're interested in, because that will tell us how the concentration of molasses and water affect the ability of these molecules to diffuse in or out down a concentration gradient. Okay, one more to go. This one's the easy one. I'm going to make one more dialysis tube bagging, but this time I'm going to use 100% molasses, 0% water. So I'm going to create that final bag. I'll be right back. Okay, here's my 100% molasses dialysis tube bag. Kind of messy, huh? So you might want to definitely have those paper towels handy. Okay, I'm going to take the initial volume of this guy using the volume displacement method and blot it dry, and then I will be ready to set these guys into my treatment cups. Be right back. Okay, so that last bag, the 100% molasses, had a volume of 10 milliliters. So that's what I figured out from the volume displacement method. So now I have all 4 of my dialysis tube bags here. Make sure you're keeping track of which one's which. So I'm going to bring the camera down here so you can see these. All right, so I'm going to take my 0% molasses and gently and quickly paste it into my 0% cup. Okay, just make sure it's all in contact with the water. I'm going to take my 25% tube, put it into the 25% treatment, make sure it's submerged, my 50% tube into the 50% cup, and my 100% tube into the 100% cup. And looks like nothing's leaking, so that's good. And now I'm just going to let these sit for 30 minutes. So time 30 minutes right now, and then come back after 30 minutes, and we're going to take a final volume of them using the volume displacement method and figure out what the change is. Okay, so I will let these sit for 30 minutes. Meanwhile, I can go ahead and start my second part of the lab, and that's the effective temperature on diffusion and osmosis. So I'm going to go ahead and let these sit for 30 minutes, and I'll be right back. Okay, so my concentration treatments that I just showed you are sitting. They have to sit there for 30 minutes. So while I'm waiting, I'm going to go ahead and set up my second part of my lab, part B of the lab, which is the effective temperature on diffusion osmosis. So for this one, you're going to need to make 3 new bags of dialysis tubing. So we have our 3 other pieces that we've cut here. And we're going to make the bags just like we did for part A of the lab, except we're going to hold concentration constant for these. We're going to have a 50-50 mix of molasses and water in each of these 3 bags. Now, I've already made mine up. So I have 3 bags here that are made up 50% molasses, 50% water. So again, we're holding concentration constant and we're looking at the effects of temperature. So I'm going to need to make 3 temperature treatments for this. I'm going to see how cold, medium, and hot affect the rate of diffusion in these dialysis tubes. So first thing I want to do is create a treatment that will be cold, specifically about 4 degrees Celsius, which is about what our refrigerators are. So you have to have a refrigerator nearby or at least some ice. So I'm going to take one of my other plastic cups here. I'm going to label this 4 degrees Celsius. And just like before, I'm going to take 100 milliliters of water and add it to here. So I'm going to use my graduated cylinder. I'm going to measure 100 milliliters of water. Get water all over my lap while I'm at it. Okay, let's see. I'm going to add the 100 milliliters of water to here. I'm going to go stick this baby in the refrigerator now because it's going to actually need to be in the refrigerator for about an hour to get to, so that the water inside will be 4 degrees Celsius. You can kind of speed up the process with some ice if you want, or stick it in a freezer for a few minutes. But if you have a thermometer, it's always good to check that it's at 4 degrees Celsius. But I'm going to go stick it in the fridge. I will be right back. I'm back. Okay, so that treatment is in the refrigerator, so it's getting to 4 degrees Celsius. I've let about an hour go by now, so it should be at 4 degrees Celsius. Next, I'm going to make my hot temperature treatment. And so for this, we're going to do 100 degrees Celsius, which is boiling. So you see back there, see if I can get this right, back there, I have my stove, and I have a trusty small pot here. And I've filled this pot about halfway with tap water. Now I'm going to use a glass, not a plastic cup, because the plastic cup will melt in the boiling water. So I'm going to use a glass. Make sure you have your goggles on. This is glass. And I'm going to pour 100 milliliters of water into my glass. So I'll measure again 100 mils with this. Add to my glass. And now I want to gently place the glass into the pot right in the middle. And now very gently, I'm going to go over to my stove here, and I'm going to put the pot on the stove, jack it up high, and let this water start to boil. Once it boils, that means that the water is at 100 degrees Celsius. Again, if you can verify it with a thermometer, that's great, but you don't have to. So follow me here. You're going to follow me into my kitchen, into the stove. You got to be careful because you should keep an eye on that boiling water. You don't want the water in the pot to boil out, so you may need to add some more water as the experiment goes on just to make sure it doesn't overboil. And don't forget to keep an eye on the time for your part A experiment. Make sure you don't go over 30 minutes. All right, the other treatment, the third treatment, is going to be at room temperature. So I have a cup here, and I'm going to label this one 25 degrees Celsius. Okay, so this is my 25 degrees Celsius, which is about room temperature, depending on your room, of course. So to be at room temperature, I'm just going to keep this one right on the table, and that will be at 25 degrees Celsius. So since it's room temperature and my water's been sitting at room temperature for a long time, this one's ready to go. So what I need to do now is, just like before, take my initial volumes of my 3 bags. Again, these are 50-50 concentrations of molasses. I'm going to use the same method. Fill this with 50 milliliters of water. Okay, and gently drop one of my baggies, and I've dried off the outside, into the graduated cylinder and see how much it went up. So this is now 60. So that means that the volume inside that bag is 10 milliliters. And I have my waste cup here. I'm going to pour that out. Okay. And I'm going to dry this with a paper towel. Okay. So this was 10 milliliters. Now I'm going to go and do the same thing with the other two. So you do the same thing with your other two. I will be right back. Okay, so I've done the volume displacement with the other two. So in total, I had 10 milliliters, 10 milliliters, and 9 milliliters for these. So now I'm ready to go. My refrigerator beaker or cup is at 4 degrees Celsius, the water in that cup. My one on the stove is boiling, so that is at 100 degrees Celsius. And of course, my room temperature one's at 25 degrees Celsius. So I'm ready to quickly drop these gently into their respective treatments. So I'm going to go ahead with the room temperature one. I'm going to go do the refrigerator one and the boiling one on the stove. And for part B of the treatment. Well, it's getting about that time where my part A is done. So I'm going to stop the watch, go back to those ones, and we're going to take the final volume measurements for part A. Okay, so I'm ready to take my final volume measurements of my dialysis tubings in the concentration experiment. So I'm going to start off with the water one. I'm going to take it out, and let's get a new piece of paper towel. I'm going to blot it dry. I'm going to take this one out, blot it dry. Remember, we don't want any water from the outside left on there because that would affect our volume measurements. So I'm going to take these out. Okay, so I have all these. Just don't forget which one's which. Move these out of the way. And now using volume displacement method, just like before, I'm going to take the final volumes of these guys. And you may even know just by looking at them that they've kind of changed shape a little bit. You know, things have moved in or out. So let's take the final measurement. So I'm going to go do that just like I did before. Fill this to 50 milliliters. Drop the dialysis tubing into there. See how much the volume rises. Subtract the difference, and you'll get the volume inside of here. So I'm going to go do that. You do. Okay, so now I'm just going to show you what your data table might look like for the effective concentration on diffusion osmosis that we just went over. So here's your lab activity handout. I'm going to scroll down to, by the way, these will remind you to take pictures along the way. So here's my data table. So this is data table A for the effects of concentration on diffusion osmosis. I recorded my initial bag volumes that I obtained through the volume displacement method for each of these concentration treatments. So you might recall I had a volume of 9 milliliters at the start of the experiment for my 0% molasses, 9 milliliters for the 25%, etc. Then at the end of the 30 minutes, I dried off my things and I used the volume displacement method again to find the volume of the bag after the experiment, so the final volume. And here are the results I got in milliliters. So what we're really interested in to determine how concentration affected diffusion osmosis is to figure out our change in bag volume. So you just subtract the initial bag volume from the final, and you'll notice 9 minus 9 is 0. So my change in volume for my 0% molasses, 100% water treatment was 0 milliliters, no change. So let's think, does that actually make sense? Well, yes, it does, because remember that osmosis is the diffusion of water from an area of greater concentration to lesser. In other words, the movement of the water molecules down a concentration gradient. Well, because there's no molasses inside that tube, only water, the concentration of water inside the tube is the same as the concentration of water outside of the tube in the cup. And therefore, the concentrations are equal, there's no concentration gradient, so there's no net movement of water molecules. It stays the same. In other words, water is in dynamic equilibrium in that treatment where there's no molasses. Now notice that my volumes start increasing as I increase the amount of molasses in the tubes. Does that make sense? For the 25% treatment, I got that the bag gained a milliliter of volume. Okay, so there's 25% molasses, 75% water. So what's going on there? Well, that means that because it's 25% molasses, the concentration of water inside the tube is less than the concentration of water outside the tube in the cup. And so by the principles of osmosis, the water is going to want to go from an area where it's more concentrated in the cup to an area where it's less concentrated inside the tube. And because this dialysis tubing has little pores that allow small molecules like water to easily go back and forth, that water is just going to simply diffuse into the tube, increasing the volume of water inside the tube. Well, now you might say, okay, but we'd expect the molasses to go outside of the tube down its concentration gradient. Well, remember that this dialysis tubing is illustrating what happens with our cell plasma membranes. They're selectively permeable. That means that large molecules can't just go in and out of that plasma membrane. They have to have help by a channel protein. Well, same thing with this dialysis tubing. It has microscopic pores, so small things like water go in and out, but large molecules like the sugars of molasses can't just do that. Most of those molasses molecules will not be able to cross that plasma membrane. They stay inside the tube. So we have the molasses still there, plus all this new water coming in, increasing the total volume inside the tube, in this case by 1 milliliter. Now when I reduce the water concentration even more and increase the molasses concentration, so now I have a 50-50 mix of molasses and water, same thing. Now there's even lower concentration of water inside the tube than outside the tube. So now water really wants to go into the tube from the outside. Meanwhile, that molasses, even though it wants to leave the tube, it can't because it's so big, so it stays inside the tube. Now I'm getting even more influx of volume into that tube. And in this case, my tube increased by 2 milliliters of volume. And finally, when there's no water in there and it's all molasses, again, that molasses can't get out, it's too big, but now there's no water in there, lots of water outside, so it's way more concentrated outside the membrane than inside. So now water is going to rush into that tube, and now we end up with a net gain of 4 milliliters of water. So, makes sense. These make sense in the light of diffusion and osmosis across a selectively permeable membrane. Okay, it's been about 30 minutes, so I'm going to go check my temperature treatments, and I'm going to treat those just like I did with part A here. I'm going to record my initial volumes here. I should have actually done that when I took them. My final volumes that I get after I take the tubes out and dry them off, and then measure the final volumes with the volume displacement method, and then calculate my change in bag volumes. And then interpret those results in light of the fact that higher temperatures mean that molecules are going to be bombarding each other faster, and they're going to bombard the plasma membrane faster. So theory says that the higher the temperature, the faster the rate of diffusion is going to be across a membrane. So we'll see if your results hold true to that. And then, of course, finally, answer the concluding questions and discuss your results, and we can help each other interpret them on the discussion board. Good to see you here, and I will see you next time. Bye-bye.